Alright, welcome back, and as promised, I'm coming at you guys with a physics problem, and we're going to be using two different methods of solving this problem, and we're going to do it the more difficult way the first time, but this is only to sort of contrast and give you a little bit of an appreciation for the alternative way of solving this problem, and that's going to be the method known as Gauss's law. And Gauss's law is one of my favorite physics sort of mathematical tricks that I've had the pleasure of using, and I hope you guys appreciate that. But to truly appreciate it, you need to see the conventional way of doing it, or at least before Gauss came along and sort of shook things up and gave a very sort of novel way of solving, problems with electric field or flux and all these different phenomena. So the problem is we're going to be trying to find the electric field at P, at point P, due to a line charge here. So we have it in the vertical position where we have y, negative y, at both ends there, right? So that's what we want to do. We want to find the electric field due to this line charge at point P. So before we start solving, let's start writing out what we know and kind of reach into our grab bag of different equations that we can use to solve this problem. So what you want to use first is the charge density equation, which essentially just tells you the charge per unit length of a line charge in this particular situation. So we're going to have that is equal to lambda, which is equal to the charge over the length, right? Okay, so we're going to use this, but we're going to sort of change the notation just a little bit, and you'll see why that becomes relevant later, but it might not seem that way right now. So for now, we're going to split this in two, right? And we're going to call each segment A. So that's A, it's negative A, right? Okay, so we're changing L to 2A, right? So that's going to give us lambda is equal to Q over 2A, right? All right, so we have that. So what we want to start doing is sort of using some of our calculus tricks in order to solve this problem, because we have just a ton of little infinitesimal little charges tucked deep within this rod that we're going to be using. So we're going to pull one of these out, right? And that's going to be D, we're going to call that dq, right? Okay, so dq, and what is it with respect to? Well, that's going to be y, right? So this is also going to be dy. My marker's given out. All right, so dy, now that's what we're going to do. We're going to take the derivative of this section right here, but first we're going to rearrange it for q. So this is going to be dq. We're going to make it lowercase now to indicate that we're using the little tiny bits of charge as opposed to the collection of charges, or an ensemble, if you will. So dq is equal to lambda. Now 2a is just going to be dy. So it may seem like kind of ridiculous that we just used it only to have it replaced, but trust me, you'll see. So this is going to be lambda and then dy, right? Okay, so that's what we're going to be using here, right? So first things first, what we want to do is start looking at the geometry of our problem and start figuring out how we can trace this electric field and sort of write out our free body diagram, right? So we're going to have, let me make that a little more bold. Now, we can obviously keep in mind that this electric field is also due to this bottom portion as well. So it's going to be, this little infinitesimal charge is going to be emitting an electric field over a distance at P. So it's going to cross or intersect, if you will, this axis. So this is going to be one of our E's. And then we have another one, right? Okay, that's another one. Okay, so that's our electric fields. Now, if you recall, any free body diagram, what you want to do is break down each of the components and decompose it. And that's what we're going to do. So we're going to take our y directions, and you'll see we have this going in the vertical, so E sub y, and then the bottom one is going in the negative direction. So due to symmetry conditions here, now we can realize these will just cancel each other out. So we don't have to worry ourselves with e sub y. We don't need the y direction, right? So that's going to just cancel. So we only need to focus on our x components. So we got x is just, they're both going in the same direction. So it's, we got e sub x here. So essentially it's more or less like this, except they're in the same placement. So, so that we're just going to treat it as one vector here. So we're going to have e sub x like so, right? So this is going to be having, this will have an angle theta with the resultant vector there, right? And that'll also become very useful very shortly. So what do we need to do here first? Well, I would recommend that we start looking at some of our equations. So we have our electric field, which is simply just E is equal to 1 over, this is our electric constant here, 4 pi times the permittivity of free space constant, epsilon naught, and that's going to be times Q over R squared, and then we have our unit vector R hat, right? Okay, so we have that all situated. What else should we do, would you think? Well, I think we should try to get a feeling for the distance, because obviously E is dependent on the distance away from where this electric field is originating. So we're going to have R, right? Okay, so we'll just call that R. And what is that? Well, as you can see here, we got ourselves a right triangle. So we're going to use Pythagoras to help us get this problem solved. So this is going to be x, right? This is going to be our x-axis, and this is going to be y. So using the Pythagorean theorem, we're going to have R is equal to the square root of x squared plus y squared. Cool. All right, so this will become very useful very shortly. So let's just kind of keep that off to the side here. And now what we want to do is kind of analyze our components here. So we're going to have some E here, right? And due to superposition, we can just sum all the vectors up. So this is going to be equal to, so actually, if we actually focus on that being our x component, that's going to be x equal to E times, well, what's the angle, right? So the angle, as you can see here, is just, it's the adjacent angle to the resultant vector. So that's always going to be cosine, right? So we're going to have E cosine of theta. Okay, so that's great. But the problem is we're not given any values. It's, we can't plug anything in. We don't know an angle, but we do know what cosine is. Cosine is just the adjacent over the hypotenuse, right? So cosine theta is going to be equal to our adjacent over our hypotenuse. And what is our adjacent? Our adjacent is x, right? So we got x over our hypotenuse, which is r. So there we go. We don't need to concern ourselves with an angle necessarily, because that's what this is. So this is what we're going to be replacing cosine theta with, right? So at this point, we can plug in our E and what we just calculated for cosine, right? So we're going to have E sub x is equal to our electric field, which is 1 over 4 pi epsilon naught times Q over r squared, and then cosine theta is just x over r, so x over r, and then we'll just do our unit vector r hat there. Okay, cool, there we go. So let's basically combine these, but then we're also going to plug in our r value, and then what we want to do is, remember, we're taking the derivative, right? So we're taking our little infinitesimal charge and analyzing the electric field due to that charge there, right? So we're going to take the derivative of this. So at that point, we'll be left with our dq, which we'll be able to plug this in for, right? So let's start sort of putting this together, right? So we're going to have, so d e, so x is equal to, well, we got 1 over 4 pi, because we got our constant here. And then combining these, we're going to have r cubed. Well, r cubed, what is that? Well, r cubed is just this raised to the 3/2. So we're going to have q, so dq over, we're going to have x squared plus y squared to the 3/2, right? Okay, and then recall we also have an x here as well, and then we got our unit vector. Okay, now let's plug in our dq, right? So that's going to give us, we're going to have 1 over 4 pi epsilon naught, and this is going to be lambda dy. So we're changing our limits here. So we're going to have lambda times, we're going to have x times over that. That's going to be x squared plus y squared to the 3/2. And then we're going to have our limit here, so dy. And great. Okay, so now at this point we have pretty much everything we need here. But at this point now we have to take into account all of the contributions here. So we're going to sum all of the little infinitesimal charges up, right? So we're going to integrate. So we're going to integrate this equation. So we're going to get, so from, so at this point, recall, with any sort of constant, you can pull that out of the integration, out of the integrand. So we're going to have, so e sub x, d e sub x is equal to 1 over 4 pi epsilon naught. And then at this point, I suggest that we take our lambda now and plug in q over 2a. So if we do that, you'll see now why we are why we changed our length to a, because that's going to be our limits of integration, right? So we're going to have this, so now plugging in for lambda q over 2a, and then we have our limits of integration. So we're going to have negative a to a, okay? So you can see how that became relevant finally. So then this is going to be x over x squared plus y squared raised to the 3/2, and that is going to be with respect to y. Okay, so this is ugly. I'm not ashamed to admit it. This is kind of a terrifying integral, but it's totally doable. So what we need to do here is realize the format of this problem and notice that this is a trig substitution problem. So acknowledging that fact, we can treat it as such. So let's start writing that out and then start simplifying it. So what we want to do is just kind of isolate this denominator so we can kind of figure out how we're going to do our substitution, right? So for this particular problem, if you recall, or even just looking up on an integral table, that we can basically treat it like the tan function, right? That's what we're going to be substituting. So we're going to have x squared plus y squared, and at this point just ignore that, the 3/2 at the moment, and you can see that this is going to end up being x squared tan squared theta, okay? So that's going to be our y, right? So let's write it out a little more formally. So y is going to be equal to x tan theta, right? And squaring it is obviously going to look like that, but we also need to take the derivative so we can replace our integration limit here. So we're going to have dy. So dy is equal to, so what is the derivative of tangent? Well, the derivative of tangent is simply secant squared. So we're going to have x times secant squared theta. So that's how this is going to go. So I would also advise that we factor out this x squared too before we start plugging anything in. So let's factor out our x squared. So we're going to have x squared, and then we're going to have 1 plus y squared over x squared. And this is all going to be to the 3/2. Okay, so that we can resolve here. This is just going to be x raised to the third power, so x cubed. So we're going to have x cubed, and that's going to be 1 plus y over x squared, and that's all we really need here. Actually, yeah, so this is going to be to the 3 halves. Okay, so we're going to be using that. So that's going to help us simplify it a bit here, right? So let's start plugging this stuff in. So we're going to have 1 over 4 pi epsilon naught times q over 2a, and we got our integral from negative a to a, right? Okay, so this x cubed is going to be below that x now. So it's going to be x over x cubed. We can just cancel that out and make it 1 over x squared. Okay, cool. So we got 1 over x squared now. And recall our new dy is going to be substituted in for, we're substituting x secant squared in for dy. So x times secant squared theta. And that's going to be over, well, what do we have here? So we factored out our x squared. We got 1 plus y over x squared. So what is y? Well, if you recall, we got y is equal to x squared times tangent squared theta. So we're going to have 1 plus, we got x squared. So x squared tangent squared theta over x squared. And then this is all with respect to d theta. So, okay, so we can cancel out our x squareds here. So that's nice. So let's get rid of that. And then let's see what that looks like. So we're going to have 1 over 4 pi epsilon naught times q over 2a. And then we got from negative a to a. And then we got 1 over x squared. Actually, keep in mind, at this point, we can cancel out our x's, right? So we'll just write 1 over x. So 1 over x times secant squared theta all over 1 plus tangent squared theta. And that is to the 3 halves d theta. Okay, so we're getting there. It's, starting to look a little more, well, a little less intimidating, rather. So if you notice, we have ourselves an identity. And I'm not just talking about my usual existential crises, but rather, I think, therefore, I have secant squared as my identity. So we're going to have that. Let's bring that over here. So equals, this is all coming over here, because this is taking up a lot of space, even with the new marker board. Oof. And 4 pi times epsilon naught times q over 2a. And then recall, now at this point, I would suggest that we just pull out that 1 over x, because that's just a constant. That's how we're treating it, as a constant. So we can pull out x, so that's going to be times x here, right? Then we have our integral, so negative a, and then secant squared over secant cubed, right? So that's what this is going to be. Secant cubed theta, after we apply the exponent there, right? So, well, what's secant squared over secant cubed? That's just 1 over secant, right? So 1 over secant theta d theta. Okay, cool. Almost there. We got this. So 1 over secant squared. What is that? Well, what is secant squared? Well, secant is just 1 over cosine theta. So we can just take the reciprocal of that and then basically just replace this with cosine. So we're going to have cosine theta. And that is a very easy integral now. I mean, the process was a little cumbersome, but now we have a very approachable integral. And what is the indefinite integral of cosine theta? Well, that's just sine theta, right? So we're going to have 1 over, that's going to be equal to 1 over 4 pi times epsilon naught times q over 2a times x. And at this point we have our limits of integration, so from negative a to a, and the integral of cosine is sine theta. And there we go. So now we just need to resubstitute back in what we substituted for in the beginning, because we can't just leave it like that, right? So we have y equals x tan theta, right? So essentially this is equivalent to y over x equals tan theta. Okay? Makes sense. So what we want to do is basically draw out ourselves a right triangle. So actually I'm going to do that over here. So we're going to have a right triangle here, right? And as we saw, we got our y and then x. And what is this right here? Well, that hypotenuse is just r. So we have r here, okay? And then it's going to be our right triangle. Okay, so now what we can do is take into account that sine theta is just the opposite over the hypotenuse. So let's see, sine theta is equal to the opposite over h, which is what? Well, opposite is y, so it's going to be y over r, and what is r? R is just the square root of x squared plus y squared. So we have the square root of x squared plus y squared. And that is what we have for sine theta. So let's just plug that back in here, right? So we're going to have 1 over 4 pi epsilon naught times q over 2a x. And that's all going to be here. So we're going to have still our limits of integration, so negative a to a. And then this is going to give us y over, that's a y, not an x, y over the square root of x squared plus y squared. Okay, so now we can just apply our limits of integration here. So at that point, this should be pretty doable, right? So now what we're going to have is obviously our constant still remaining outside here. So 4 pi epsilon naught times q over 2ax. And we're going to have, all right, so a is going to substitute in for y, right? So we're going to have a over, that's going to be x squared plus a squared now, right? So this is going to be x squared plus a squared minus, well, we got a negative a, so it's going to be minus minus, so that's going to be plus, so plus a over the same thing, right? Because the squared will just get rid of that negative sign there. So x squared plus a squared, right? Okay, so now we can just add these together, and we're going to have 1 over 4 pi times epsilon naught times q over 2a times x, and that's going to be times 2a over the square root of x squared plus a squared. And now we can just cancel out 2a. So that's pretty nice. So cancel out 2a, and we're going to have 1 over 4 pi epsilon naught times q. Actually, we'll just put q here. We'll put q here. And it's going to be x times 1 over square root of x squared plus a squared. Okay, so that's pretty nice. Okay, so now we have our electric field, and let's sort of deconstruct this and rearrange it to get a little bit of a better sort of idea as to what it's telling us. So we're going to have this equal to 1 over 4 pi epsilon naught. So what we want to do is factor out an a squared from that radicand. So that's going to be a squared factored out, and we have to do x over a, we'll have that squared, right, plus 1. Okay, so that a squared is just going to become a. So what we're going to be left with here is 1 over 4 pi epsilon times q over a, and that's going to be times 1 over x square root of x squared over a squared plus 1, right? So it still may not look like a whole lot, but let's borrow a 2 from this 4 pi here and put that right in front of the a. So that's going to be equal to now 1 over 2 pi epsilon naught times q over 2a times 1 over x square root of x squared over a squared plus 1. Okay, so x or q over 2a is simply what we had here. It's just our line charge density. So we can just replace that with lambda. So we're going to have now 1 over 2 pi epsilon naught times lambda over x square root of x squared over a squared plus 1. Okay, so now we have that all situated. Let's sort of analyze what would happen if, say, a was really, really large. So if a was really large, so in terms of, in relative to x, that is, so if a is really, really large, larger than x, well, we can basically ignore this whole portion here. So you're dividing by a really large number, and as it gets infinitely large, that's just going to tend towards 0. So we can basically ignore that part. So we'll end up having just, if this condition is met, we're going to have lambda over 2 pi epsilon naught times x, right? Because that's just going to be just x times 1 at that point, right? So there we go. So what is this telling us? Well, when a is really, really large, or the segment is infinitely large, then it's going to have an electric field of a strength magnitude that travels by 1 over x as opposed to 1 over x squared, which is maybe a little strange, but over short distances, it's really not that, it's almost negligible at that point. If it were to be infinitely large, obviously there's not really such a thing as an infinitely large line charge, but think of it in this way. So if x here is much larger than a, we're going to have 1 over 2 pi epsilon naught. Well, if x is really large, then we do have to consider x squared. And we can almost ignore a squared then. So think of it just as the square root of x squared, and then we have x times x. So we are back to our normal convention, which gives us x squared. So that's, what you would generally expect whenever the distance is over an infinitely large range. So with that in mind, this is, makes perfect sense, because obviously up to smaller distances, the electric field doesn't exhibit that property quite like it does in longer distances. So in that sense, you can think of it also with like an insulator. If you had an insulator with a net electric charge within the insulator, well, obviously it wouldn't work with a conductor because the electric field inside of a conductor is 0. But with an insulator, it travels linearly until it reaches the radius of that sphere within an insulator. once it hits that radius, it begins to travel by the distance squared. So it's kind of a similar idea, but it sort of illustrates what happens whenever you kind of change some of these parameters. But with that in mind, this was obviously very cumbersome, and I apologize if that was overwhelming, but it will surely give you a much, much broader appreciation for Gauss's law when I show you the alternative method for solving this problem. So stay tuned, and I will be coming at you with a new and improved edition of this just chaotic mess. So thank you for watching.